Hello everyone! Today we're going to explore a powerful problem-solving technique that sounds a little intimidating, but is actually quite intuitive once you get the hang of it. It's called dynamic programming. Now don't let the name fool you. It doesn't have much to do with dynamic in the way we usually think of it, like an exciting action movie. Instead, think of it as a smart and methodical way to tackle complex problems. It's a method that computer scientists and programmers use to make their programs faster and more efficient. By learning this technique, you are adding a major tool to your problem-solving toolkit, one that can be applied to many different challenges you might face in mathematics, computer science, and even in real-life planning. So, what is dynamic programming at its heart? It is essentially a strategy for breaking down a large, complicated problem into smaller, more manageable pieces. The key insight is that the solution to the big problem often depends on the solutions to these smaller sub-problems. Instead of solving the same small problem over and over again, we solve it just once and save the answer. The next time we need that same answer, we don't have to do the work again, we simply look it up. This simple idea of remembering past results can lead to dramatic improvements in speed, turning a program that might take years to run into one that finishes in a fraction of a second. Imagine you are assembling a very large and intricate Lego model. You wouldn't try to build the entire thing all at once in a chaotic fashion. Instead, you would likely follow the instructions, which guide you to build smaller sections first, a wheel assembly here, a cockpit there. Each of these smaller sections is like a sub-problem. Once you've built a section, you set it aside. When you need that specific component later for the final assembly, you don't rebuild it from individual bricks. You just grab the completed section. Dynamic programming works in a very similar way. It's a disciplined approach that builds up a solution from the bottom, ensuring that no work is ever repeated unnecessarily. This technique is incredibly useful in a wide range of applications. It's used in everything from creating algorithms that tell your GPS the shortest route to a destination, to figuring out the most efficient way to schedule tasks, to analyzing DNA sequences in bioinformatics. It's a fundamental concept in computer science because it embodies the principle of efficiency. By learning to recognize when and how to apply dynamic programming, you will be able to write code that is not only correct, but also elegant and performant. So, let's get ready to dive in and see how we can master this powerful method, one step at a time. We'll start with the basic ideas and build up to a solid understanding. The fundamental principle behind dynamic programming is beautifully simple. Solve a complex problem by breaking it down and solving its smaller sub-problems first. Think of it as a strategy for not repeating yourself. Many big problems are really just collections of smaller, similar problems. For instance, to calculate the best way to invest money over 10 years, you might first need to know the best way to invest it for 9 years, which in turn depends on the best way to invest for 8 years, and so on. You can see a pattern emerging here. The main problem is built upon the solutions to slightly simpler versions of the same problem. This is the kind of structure where dynamic programming truly shines. This idea of breaking things down is something we do naturally in everyday life. If you were asked to climb a tall ladder, you wouldn't try to jump to the top rung in one giant leap. Instead, you would climb it step by step. Each step you take is a small, manageable action. Reaching the 10th rung is only possible because you first reached the 9th, which was possible because you reached the 8th. Each step is a sub-problem, and the solution to reaching the top is a sequence of solutions to these smaller sub-problems. Dynamic programming formalizes this intuitive process for computational problems, giving us a structured way to build up to a final answer without getting lost in the complexity. For dynamic programming to be a suitable strategy, a problem must have two specific properties. The first is called overlapping subproblems. This just means that the same subproblems are encountered multiple times as we try to solve the larger problem. Instead of recomputing the solution to these subproblems every time they appear, we can calculate them once and store the result. This act of storing results for later use is the magic that makes dynamic programming so efficient. It saves a tremendous amount of computational work by avoiding redundant calculations. which is a common source of slowness in many simple or naive algorithms. The second key property is known as optimal substructure. This sounds complicated, but the idea is straightforward. It means that the optimal solution to the overall problem can be constructed from the optimal solutions of its subproblems. Let's go back to our ladder example. The best way to get to the top rung is to find the best way to get to the second to last rung, and then take one more optimal step. If the solution to the big problem can be built by combining the best solutions of its smaller parts, then the problem has optimal substructure. When a problem has both overlapping subproblems and optimal substructure, it's a perfect candidate for a dynamic programming solution. To truly master dynamic programming, we need to get comfortable with the concept of subproblems. What exactly are they? Subproblems are simply smaller or simpler versions of the original larger problem you are trying to solve. The smaller aspect could mean many things. It could refer to a smaller input size, a shorter time frame, or a smaller number of items to consider. For example, if the main problem is to find the shortest path from point A to point Z in a large network of cities, a subproblem might be to find the shortest path from point A to some intermediate city, like point M. The solution to the larger problem likely involves passing through one of these intermediate cities. Identifying the right subproblems is often the most challenging part of applying dynamic programming. It requires you to look at the problem and think, how can I define this problem in terms of a variable, say such that the solution for depends on the solutions for values smaller than? This is the creative leap that unlocks the path to a solution. You need to find a relationship, often called a recurrence relation, that connects the solution of a problem of a certain size to the solutions of smaller-sized problems. Once you find this relationship, you have a clear roadmap for how to build your way up to the final answer. Let's consider an example. Imagine you want to calculate the total number of ways you can climb a staircase with steps. If you can only take 1 or 2 steps at a time, the main problem is to find the answer for steps. A subproblem would be to find the number of ways to climb a staircase with fewer steps, say, or. To get to the third step, you must have come from either the third step, by taking a single step, or the third step, by taking a double step. Therefore, the total number of ways to reach step is the sum of the ways to reach step and the ways to reach step. This is our recurrence relation. This relationship between the main problem and its subproblems is the engine of a dynamic programming solution. It tells us exactly how to solve a bigger problem if we already know the answers to the smaller ones. We also need a base case, which is a subproblem so simple that we can answer it directly without any further calculations. In our staircase example, the base cases would be media group, student standing still at bottom of staircase, teacher writing 0 steps, =, 1 way on classroom board at stock at distribute _ equally, the number of ways to climb 0 steps, 1 way, just stand there, or 1 step, 1 way, take a single step. With the base cases and the recurrence relation, we have everything we need to solve the problem for any number of stairs, no matter how large. Now, let's make this more concrete with one of the most famous examples used to introduce dynamic programming, calculating the Fibonacci sequence. The Fibonacci sequence is a series of numbers where each number is the sum of the 2 preceding ones. It typically starts with 0 and 1. So the sequence goes 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. The rule, or the recurrence relation, can be written as fib of n equals fib of n minus 1 plus fib of n minus 2. Our goal is to write a function that, given a number n, can calculate the nth Fibonacci number. This problem is a perfect illustration of the principles we've just discussed. Let's analyze this problem in the context of dynamic programming. Does it have optimal substructure? Yes. The solution for fib of n is built directly from the solutions of its subproblems, fib of n minus 1 and fib of n minus 2. Does it have overlapping subproblems? Absolutely. To see this, let's think about calculating fib of 5. According to the rule, fib of 5 equals fib of 4 plus fib of 3. Now let's expand that further. Fib of 4 equals fib of 3 plus fib of 2, and fib of 3 equals fib of 2 plus fib of 1. Notice anything? To calculate fib of 5, we need to calculate fib of 3 twice. If we were calculating fib of 10, we would end up recalculating fib of 5, fib of 4, fib of 3, and so on, many times. This repetition is where the inefficiency lies. If we just write a simple function that calls itself based on the rule, it will work. But it will be incredibly slow for larger values of n. For each increase in n, the number of calculations grows exponentially. This is because our simple function has no memory. Every time it's asked to compute, say, fib of 3, it starts the calculation from scratch, even if it just did the exact same calculation a moment ago as part of a different branch of the computation. This is what we call a naive recursive approach, and it's a trap that many people fall into when they first start. The dynamic programming approach offers a way to escape this trap. It acknowledges the overlapping subproblems and introduces a mechanism to avoid recomputation. Instead of forgetting the results of our subproblems, we will store them. The first time we calculate fib of 3, we'll save the answer. The next time anyone asks for fib of 3, we won't recalculate it. We will simply retrieve the stored value and return it instantly. This simple act of remembering transforms the problem. It turns an exponential time nightmare into a linear time, highly efficient solution. Let's explore exactly how we can implement this memory. To fully appreciate the power of dynamic programming, it's helpful to first look at the straightforward or naive way of solving a problem and understand why it can be inefficient. For the Fibonacci sequence, the most direct translation of the mathematical formula, which is fib of n equals fib of n minus 1 plus fib of n minus 2, into code is a recursive function. A recursive function is one that calls itself. In this case, our function fib of n would call fib of n minus 1 and fib of n minus 2, and then add their results. We would also define our base cases. If n is 0, the function returns 0, and if n is 1, it returns 1. This seems perfectly logical and elegant. Let's trace what happens when we try to compute fib of 6 with this naive approach. The function fib of 6 calls fib of 5 and fib of 4. Then, fib of 5 calls fib of 4 and fib of 3. Right away we see a problem. Fib of 4 is being called twice, once by fib of 6 and once by fib of 5. Each of these calls to fib of 4 will then trigger its own cascade of calls, fib of 3 and fib of 2. This creates a massive branching tree of function calls. The amount of redundant work is, honestly, staggering. The function recomputes the same Fibonacci numbers over and over again, completely unaware that it has solved these exact same subproblems moments before in a different part of the call tree. The consequence of this repeated work is a dramatic slowdown. While calculating fib of 5 or fib of 6 might seem fast enough, try calculating fib of 40 or fib of 50 with this method. Your computer will seem to freeze, taking a very long time to return an answer. The number of operations required grows exponentially with n. This is because each call to fib of n generates roughly 2 more calls, leading to a tree of calls that grows incredibly wide at its base. This is a classic example of an algorithm with a poor time complexity, specifically exponential time, often written as O of 2 to the power n. For practical purposes, such algorithms are unusable for anything but small inputs. This is precisely the problem that dynamic programming is designed to solve. The naive recursive solution is beautiful in its simplicity, but fails in its performance because it wastes effort. It resolves the same subproblems repeatedly. The realization that this waste is happening is the first crucial step toward finding a better way. We need a method that combines the logical clarity of the recurrence relation with a mechanism for efficiency. We need a way to remember the answers to the subproblems we've already solved, so we can look them up instead of recomputing them. This leads us directly to our first dynamic programming technique, memoization. Now that we understand the problem with the naive recursive approach, let's introduce our first dynamic programming strategy, memoization. The word might sound fancy, but the concept is very simple. It's just about remembering or memoizing the results of function calls so that we can reuse them later. Think of it as creating a cheat sheet or a lookup table for our function. Before our function does any heavy lifting to compute an answer, it first checks this table. If the answer it needs is already there, it just returns it immediately. If not, it computes the answer. And, this is the crucial part, it stores the new answer in the table before returning it. Let's apply this to our Fibonacci function. We can use an array or a hash map, which is often called a dictionary, to act as our cache or memory. Let's call this. We initialize this table, perhaps filling it with a special value like -1 to indicate that no results have been computed yet. When our function is called, the very first thing it does is check. If the value is not -1, it means we've already computed before, so the function can just return without any further calculation. This simple check is what prevents the explosive chain reaction of redundant calls we saw earlier. If the check fails, meaning is still -1, then our function knows it has to do the work. It proceeds just like the naive recursive function by calling itself to compute and. But here's the key difference. Once it gets the result by adding those two values, it doesn't just return it. First, it stores the result in its memory. Then, it returns the result. This ensures that the next time the function is called with the same input, the initial check will succeed, and the computation will be skipped entirely. This technique is also known as a top-down approach. This simple addition of a cache completely changes the algorithm's performance. Let's go back to our example. The first time the function needs to compute, it will do the work and store the answer. A moment later, when another part of the call tree asks for again, the function will find the answer in its cache and return it instantly. All the redundant branches of the call tree are pruned away. Instead of the number of operations growing exponentially, it now grows linearly with. We only compute each Fibonacci number from up to exactly once. This is a massive improvement and demonstrates the core power of dynamic programming. Memoization, or the top-down approach, is a great way to implement dynamic programming. But there is another, often more efficient way called the bottom-up approach, also known as tabulation. Instead of starting from the top, that we want to solve, and breaking it down recursively, the bottom-up approach starts from the bottom, which is the simplest base cases, and builds its way up to the final answer. It solves the sub-problems in a specific order, from smallest to largest, and stores their results in a table, hence the name tabulation. This way, whenever it needs to solve a particular sub-problem, it knows that the solutions to all the smaller sub-problems it depends on have already been computed and are ready in the table. For our Fibonacci example, the bottom-up approach is very intuitive. We know we need to compute. We also know that is 0 and is 1. These are our base cases, the smallest subproblems. So we can create a table, let's say an array called of size, to store the Fibonacci numbers. We start by filling in the known values, and now we have the foundation we need to build upon. We have solved the smallest subproblems first. Next, we can simply loop from up to. In each step of the loop, we calculate the Fibonacci number using the values we have already computed. The formula is, since we are iterating from 2 upwards, when we are at step, we are guaranteed that the values for and are already computed and stored in our table. We continue this process, filling the table one spot at a time, until we reach. The final answer to our problem is simply the value stored at. This bottom-up method is often preferred for a few reasons. First, it avoids recursion, which can sometimes lead to issues like exceeding the maximum recursion depth for very large inputs. The iterative approach of using a loop is typically a bit faster in practice because there is no overhead from function calls. Second, the logic can sometimes be easier to reason about, as you are explicitly building the solution from the ground up in a clear, sequential order. You can visualize the table being filled, which makes the process very transparent. Both top-down with memoization and bottom-up with tabulation are valid dynamic programming techniques, and they will solve the same set of problems. As you begin your journey with dynamic programming, you're likely to encounter a few common hurdles. One of the most frequent mistakes is identifying the sub-problems incorrectly. Students often struggle to define the state of their DP solution. The key is to think about what information you need to carry forward to solve a larger version of the problem. Ask yourself, what are the variables that define a subproblem? For Fibonacci, it was just the index. For other problems, it might be 2 variables, like a starting and ending index or a current weight capacity. Practice is the best way to get better at recognizing these patterns and defining the states correctly. Another common pitfall is getting the recurrence relation wrong. The recurrence relation is the heart of your DP solution. It's the formula that connects the sub-problems. If this formula is incorrect, your entire solution will fail. A good way to avoid this is to work through a small example by hand. Try to solve the problem for or manually, and pay close attention to how you are using the results of smaller cases to find the answer for the larger case. This manual process will often reveal the correct relationship between the problem and its sub-problems, helping you formulate a correct and reliable recurrence relation. Forgetting the base cases is another classic error. Your recurrence relation needs a place to stop. Without proper base cases, a recursive solution will run forever or until it crashes, and a bottom-up solution won't have a foundation to start building from. Always explicitly define the simplest possible sub-problems, the ones you can solve instantly without any further calculation. For Fibonacci, these were and. For a staircase problem, it might be the number of ways to climb 0 or 1 step. Double-check that your base cases are correct and sufficient to handle the smallest inputs your function might receive. Finally, a subtle mistake is choosing an inefficient data structure for your cache or table. For the Fibonacci problem, a simple array was perfect because the sub-problems were indexed by integers 0, 1, 2, up to. However, some problems might have sub-problems defined by pairs of numbers or even strings. In these cases, a hash map or a dictionary might be a much better choice for your memorization cache. Using the wrong data structure can make looking up results slow, which can undermine the very efficiency gains you are trying to achieve with dynamic programming. Always consider the nature of your sub-problem state when choosing how to store your results. As we wrap up our exploration of dynamic programming, let's summarize the most important points to remember. Think of this as a checklist you can use whenever you encounter a problem that seems like a good candidate for this technique. First and foremost, remember what dynamic programming is all about. It's a method for solving complex problems by breaking them down into simpler, overlapping subproblems. The core idea is to solve each subproblem only once and store its result, so you never have to recompute it. This principle of remembering is what gives DP its power and speed. Second, always check if the problem has the two key properties required for dynamic programming. Ask yourself, does this problem have overlapping subproblems? That is, will a naive recursive solution end up solving the same smaller problems over and over again? And second, does it have optimal substructure? This means, can the optimal solution to the big problem be constructed from the optimal solutions of its smaller parts? If the answer to both of these questions is yes, then dynamic programming is very likely the right tool for the job. Recognizing these two properties is the most critical step in the process. Third, once you've determined that DP is a good fit, your next task is to find the recurrence relation and identify the base cases. The recurrence relation is the mathematical formula that defines how a problem of size is related to its subproblems. The base cases are the smallest, simplest instances of the problem that you can solve directly. These two components together form the complete logical specification of the solution. Spend time getting these right, perhaps by working through small examples by hand, as they are the blueprint for your code. A mistake here will lead to an incorrect solution. Finally, remember that you have two main strategies for implementing your solution: top-down with memoization or bottom-up with tabulation. The top-down approach uses recursion and a cache to store results as they are computed. The bottom-up approach uses iteration to fill a table starting from the base cases and building up. Both are powerful, and choosing between them can sometimes come down to personal preference or the specific constraints of the problem. By keeping these key ideas in mind, you'll be well equipped to start identifying, analyzing, and solving a whole new class of challenging and interesting problems. Keep practicing, and you'll master it in no time.